My name is Dr Michelle Dickinson. I've learnt that breaking things down is the easiest way to understand them. So join me. We'll break down scientific concepts, meet some amazing scientists and inventors, and help you discover the world around you.
Kia ora. I'm Dr Michelle Dickinson, and today we're going to be talking about climate change. When we talk about climate, we usually refer to the average of meteorological elements like wind, rain, and temperature that we can measure over many years. When we talk about climate change, we're looking for significant changes in our climate that occur over several decades or even longer. Knowing the science behind some of the changes that have occurred in our climate helps us to understand how and why it might change in the future. To help us understand climate change as a concept, today we are going to talk about the difference between climate and weather. Then we will look in more detail about some of the products and technologies that humans make and think about whether they might be affecting our climate. We'll also do an experiment to show how sea creatures, especially those that make hard shells, might be affected by changing acidity in the ocean, which is also to do with our changing climate. To do the experiment with me, you will need a raw egg, a glass, and some clear vinegar. Also, you'll need your notebook and pen so that you can write down your observations. If you haven't got those things to hand, go grab them now. A bit later in the show, I'll be checking in with one of my science helpers who'll be joining us from home and speaking to one of my friends who'll be able to tell us even more about their research into climate change. Okay, let's get started. Many people use the word climate to describe the weather, but actually they are two different things. Weather is a description of the state of the atmosphere at a particular time and place. We can describe the temperature as a function of how hot or cold it is, or how much precipitation, like rain, snow, or hail, there is. We could create a log of the local weather by measuring it every hour or every day, and if we did this over 30 years, then we could start looking at the weather from a climate perspective. The climate, ahua o te rangi, describes the typical weather conditions averaged over a long period of time. So the climate of a place can be temperate, cold, or even tropical. When we talk about climate change, we aren't looking at how one summer might be warmer than the one before it, but instead how on average the last 30 summers might be warmer than the last 50 that have gone before them. So how do we know what weather to expect? Well, luckily, we have been measuring and recording data about the Earth's weather for hundreds of years. But how do we know about what the Earth's climate was like before we started taking records? Well, we can also tell a lot about our planet and what it might have been like through fossils. For example, fossilized wood and pollen from plants have been found in Antarctica. And by dating these, we can tell that between 145 and 65 million years ago, the climate in Antarctica was warm enough for trees to grow. Because there are no trees growing in Antarctica anymore, we can conclude that the climate of Antarctica is very different now to how it was millions of years ago. By looking for fossils in thousands of locations, we have been able to model the Earth's climate over long periods of time. We know that the Earth's climate has naturally warmed up and cooled down many times throughout history. The Ice Age, for example, is how we describe periods of time in the Earth's history when global temperatures are relatively cold, resulting in thick ice sheets covering vast areas of land. There have been at least 5 major ice ages throughout the Earth's history, and they have lasted millions of years and dramatically reshaped the surface features of whole continents. Scientists believe that these prolonged warm and cold periods that occur in regular patterns, and they're called Milankovitch cycles, occur due to changes in the Earth's orbit around the Sun. We also know from looking at these long-term cycles that levels of some greenhouse gases, including carbon dioxide and methane, also move up and down with global temperature. As a general rule of thumb, when greenhouse gases have naturally been high, the Earth has been warmer, and when they were low, the Earth has been colder. You may have heard climate change being talked about a lot recently in the media, and that's because we are currently experiencing changes in our climate that seem to be happening much faster than before. They're also different to what was predicted to happen naturally. As scientists, we need to ask why this may be happening differently to how we thought, and if there are any things that we can measure to help us come up with a conclusion. One of the things that has definitely changed over the last 2 centuries is the way that humans produce and consume things. Known as the Industrial Age, this period of time transformed economies from agriculture and small-scale businesses to large-scale factory systems that incorporated new power sources and mechanized ways of making things. One of the consequences of these technologies is that they produce a series of greenhouse gases, such as carbon dioxide, which can collect in our atmosphere. Many of these industrial technologies have been fueled using fossil fuels, like oil, coal, and gas. These types of fuels are made from plants and animals that died millions of years ago and over time were pressed together and fossilized into a carbon-rich mixture. When fossil fuels are burnt in oxygen, they produce energy, which we use to power machinery. And they also release carbon dioxide as a byproduct. Now, not all carbon dioxide has been produced by industry. Naturally produced carbon dioxide also exists, and it makes up about 0.04% of all of our gases in the atmosphere. It's produced by animals as they breathe out, as well as volcanic eruptions. Carbon dioxide, along with some other gases in our atmosphere, can prevent the sun's heat from leaving the Earth and escaping out into space. Acting a bit like a blanket over the Earth, these gases keep the heat in. With so much of it now being released from activities like burning fossil fuels, too much heat is being trapped in our atmosphere, which is a phenomena that we know as the greenhouse effect. Through detailed records, we have seen that since 1900, the Earth's climate has heated up on average by 1 degree centigrade. Now, on a cold day, you might think that more warmth is a good thing. But as we know, warm weather is a very different thing from a warm climate. And a warmer climate can have a huge effect on the Earth and the animals and the plants that live on it. The North and South Pole of the Earth are covered in ice. When the Earth warms, the ice melts, and all of this extra water ends up in the ocean. This increase in liquid water from the solid water that it came from causes sea levels to rise. Rising sea levels can threaten communities and infrastructure that are built near coastlines. In the last century, the sea level has risen between 14 and 22 centimetres. This is important to know, so that our coastal communities can plan for the fact that they will continue to lose land between themselves and the sea. While carbon dioxide in the atmosphere is one challenge, carbon dioxide in our oceans is another. The carbon dioxide that is not in the air gets absorbed by the moana, or the ocean. When carbon dioxide dissolves in water, a new substance is formed, called carbonic acid. As the concentrations of carbonic acid in the ocean increase, it causes the ocean to become more acidic. This process is called ocean acidification. For millions of years, seawater had a pH between 8.1 and 8.2, which makes the ocean slightly alkaline or basic. However, the extra carbonic acid is changing this. Scientists predict that by the end of this century, the pH in some parts of the ocean would have dropped to somewhere between 8 and 7.7. Many of the creatures that live in our oceans have structural elements that are made of calcium carbonate. These include shells and corals. Carbonic acid dissolves calcium carbonate, making shells thinner and more fragile. Ocean acidification, therefore, can make a real difference in the life cycles of many of our marine creatures. As we're talking about ocean acidification, why don't we try and visualize this better with an experiment to demonstrate the effects that an acidic ocean could have on shells. Hi Amelia, how are you?
Hi, I'm good, thank you. How about you?
I'm good. Thank you for helping with the experiment today. Can I just check that you have an egg, a glass, and some vinegar?
Yep.
So we're talking about the climate and how the climate changes. Now, it's not often that an egg and some vinegar come together, but actually eggshells are really interesting because they're made out of calcium carbonate. And that's the same material that seashells are made out of. And I couldn't find any seashells, so we found a close cousin, which is the eggshell instead. So what I'm going to ask you to do is put your egg carefully into the glass, trying not to crack it. So we're going to make a prediction first. We're going to pour the vinegar on top of the egg. Do you know what might happen?
Well, vinegar's an acid, but I'm not too sure what it'll do.
Very good. So vinegar is an acid. So when we look at the pH scale, vinegar comes in around 2 or 3, depending on the strength of your vinegar. And so when we talk about ocean acidification, what we know is that our oceans are becoming slightly more acidic. And so what we're going to do here is an experiment that shows you what happens when calcium carbonate, which is eggshells and seashells, come into contact with an acid. So we're going to pour the vinegar on top and let's see what happens. Okay, now take a look very closely at your eggshell. Can you see anything forming on the surface of your eggshell?
Oh, there's lots of mini bubbles.
So those mini bubbles are actually carbon dioxide. And what's happening is the shell is starting to be dissolved by the acid. And so the calcium carbonate that we have is starting to dissolve, and that is producing these bubbles of carbon dioxide. Now, this is not good for the eggshell. And do you think it's good for seashells?
No.
No, it's not good for seashells. And we know that as our oceans become more acidic, our seashells are starting to get a little bit softer. And so what's happening is they're dissolving in the acid. Now, oceans are nowhere near as acidic as vinegar, so this is a very extreme reaction. But what do you think might happen to sea creatures if their shells start to get soft?
They could die.
Yeah, they could die. And if you think of some of their predators, like maybe a seagull, they're going to be able to tap into a seashell much more easily and eat what's on the inside. But also, in acidic sea conditions, it's actually more difficult for the creatures to make their shells. And so it's not just about them being more vulnerable, but also them making smaller shells. And that is bad for the ocean. And so as we think about having more acidity in our ocean, meaning it's closer to vinegar, although never as extreme as vinegar, we can see the effects on our sea creatures. And it's not a good effect, sadly, but it's a very visual way of showing you how seashells and eggshells dissolve in acid. Well, Amelia, thank you so much for helping me today.
Thank you for having me.
Okay, after any experiment, we need to write down our observations. These help us to understand our results and make interesting predictions for our next experiments. So, observations. What did we see? We saw that as soon as we put the egg into the vinegar, there were bubbles of gas coming off the egg that rose to the surface. We also saw that within a few minutes, the bubbles started to get larger. Now, we know that the eggshell is made of calcium carbonate, and that when calcium carbonate is mixed with an acid, it dissolves, producing carbon dioxide gas, which is what we saw in the bubbles. Next, we look at our observations and reflect on them. By asking questions about why something happened, or how we might make it happen again, we're really starting to understand the science behind it. For example, we could do this experiment at different temperatures and see if it makes a difference to how fast the carbon dioxide bubbles start forming. Or we could try it with an actual seashell instead of an eggshell and see if the same reaction occurs. Okay, now we have a little bit more understanding about how carbon dioxide affects the atmosphere and the ocean. We're going to talk to somebody who researches what our climate was like in the past. Professor Tim Naish works at the Victoria University of Wellington, where he researches how we can use evidence from our past to predict what the climate will be like in the future. Hi Tim, how are you?
Yeah, hi Michelle. Very good. Excited to be on your show.
That's good. For everybody at home, can you just introduce yourself, please?
My name's Tim Naish. I'm a geologist and a climate scientist. I'm a professor at Victoria University of Wellington. I do a lot of my science in the Antarctic, and I'm really interested in how the Antarctic has changed in the past and how it might change in the future with global warming and what this means for us and our planet's climate.
Tell me about your lab then. Do you have a lab in Wellington or in Antarctica or both?
I don't specifically have a lab myself. I'm very lucky. I have a time machine. So what I've been doing a lot of my life is drilling holes through the ice and into the rocks and the sediments under the ice. So my time machine allows me to go back in time and to see what the world was like. The rocks form in layers. They're very much like a history book, and you can read through the book and you can read the layers of the history of the Earth. And we can use very clever techniques, like we can use fossils, we can use small microfossils, marine fossils, algae that lives in the ocean and dies, or we can use the pollen from plants that once grew on the land to reconstruct what the environment was like and what the climate was like and how big the ice sheet was and how high sea level was from this amazing information that is preserved as layers in the geological record.
So I think everybody wants a time machine. How far back in time can you go?
I mean, the Earth is 4.5 billion years old. And I know that seems really hard to comprehend, but the period I'm interested in is like the last few minutes before midnight, if you considered the time on a clock from 1 o'clock all the way around to 12 o'clock as geological history. I'm interested in the very last few minutes of geological history, which is the last 5 million years.
What do you enjoy most about your job?
As scientists, we're really learning things about our planet that are important for society. And climate change is one of those big, big questions, those big things we are facing. And I know COVID-19 is really big, and we're facing that right now. But as we recover from COVID-19, and it will take some time, climate change continues to be one of the number one issues we're going to have to deal with as scientists.
So there are going to be students who are watching this today who want to do something about climate change. Is this something that we as individuals can do something about?
Oh, absolutely. It seems at times a really big problem that we have no control over, but that's not true. The science tells us that there is still time to keep global warming to a level that will prevent really bad things happening with the climate, things we don't want to have, like really big sea level rise and major worldwide droughts and wildfires and that sort of thing. There's still time. And so that's where we all have a role to play. I mean, people in their daily lives, and I think, COVID-19 has showed us this. We don't need to drive as much as we used to do. We don't need to fly as much as we used to do. We can live a life where our carbon footprint, the amount of greenhouse gases we put in the atmosphere, is greatly reduced.
Before we go, Tim, this has been fascinating, but do you have one awesome fact that you would like to share with everybody about your research field?
I do. I think one of the most awesome things is about water. From all the global warming we've done so far, since we've been burning coal, oil and gas, 93% of the heat from that global warming has gone into the ocean. So the world is only warmed by 1 degree. If we didn't have the ocean, the world would have warmed by 35 degrees. It has protected us so far from really bad global warming.
Tim, it has been fascinating. Thank you for helping us with our climate change research and also for inspiring the next generation to help the planet.
That's been a pleasure.
we have learned how some of the carbon dioxide produced can be absorbed by our oceans. We refer to our ocean as a carbon sink. Another powerful natural carbon sink that we have are our forests. Plants absorb carbon dioxide from the air for photosynthesis. This means that large forests are areas of concentrated carbon absorption. Together, our global forests and oceans absorb about 2/3 of all of the carbon dioxide produced every year. We've already talked about what happens to carbon dioxide in the ocean and the effects that it can have on the shells of marine animals. One of my favourite sea creatures is the kinner, or sea urchin. Now, urchins have hard shells made of calcium carbonate, similar to eggshells. You might not think so, but urchins actually have a set of rasping teeth in a small mouth right in the middle of the underside of the animal. These teeth are also made of calcium carbonate, and each tooth acts like a sharp scraper, scraping away at their favourite foods like kelp and algae on rocks. Those teeth become brittle and quickly wear away at high carbon dioxide levels. This makes it harder for the urchins to eat. It's difficult to make predictions about what's going to happen to a particular animal in the future, because not every single animal in a population will respond exactly the same way. Some species will also be more resilient than others, but we think that sea urchins might be one of the vulnerable animals in the ocean. So currently there is a lot of research being done by marine scientists to understand all of the different ways that climate change may affect their life cycles. We're all going to feel the effects of climate change in our lifetimes, and it's a topic that brings up the need for hard conversations and some uncomfortable emotions. But our emotions can spur us into action, and when our actions are based on scientific evidence, we can make such a difference in the world. Now you know more about the science of climate change. What actions could you take that might help to reduce the amount of carbon dioxide that we release? It might be planting trees, growing a vegetable garden, riding a bicycle, or using public transport to get around. You could brainstorm more ideas and maybe come up with a top 3 that you can all work on together. Lots of small changes add up to big world-changing effects. You literally can change the world, one small action at a time. Teachers and parents, don't forget to visit nanogirlslab.com, where we have downloadable content to help you continue on your science journey into our changing climate. Thanks for watching. Where on Earth is global warming happening fastest? What happens to the deserts if they get hotter? Will I still be able to go on holiday to my favourite destination? How do we stop rising seas from flooding our houses? Will planting more trees take more carbon dioxide from the atmosphere? Will higher sea levels mean that beaches will disappear? What can I do to help mitigate the effects of climate change? How can I calculate my carbon footprint?